everybody, Mrs. Pesic here.
And Miss Bella here.
And we are looking at section 9-2, series and summation notation. The objectives to evaluate the sum of a series that's expressed in sigma notation. Our vocabulary, series, partial sum, and summation notation. In lesson 9-1, you learned how to find the nth term of a sequence. Often we are also interested in the sum of a certain number of terms of a sequence. So a series is that indicated sum of the terms of a sequence. Here are some examples. If a sequence is 1, 2, 3, 4, the series would be 1 plus 2 plus 3 plus 4. If the sequence was 2, 4, 6, 8, ... goes on forever and ever, the series would be 2 plus 4 plus 6 plus 8 all the way up. And you could even add fractions, 1/2. If the sequence is 1/2, 1/3, 1/4, 1/5, 1/6, then the series would be adding all of those together.
Because many of our sequences are infinite, which would be like this middle example up there with that ... after the 8. So talking about that one would be infinite. And do not have a defined sum, we often will find partial sum. So a partial sum is indicated by S sub n. And that is the sum of a specified number of terms of a sequence. So just an example here to kind of clarify that. So for the even numbers, so if I did the sequence of even numbers, well, that would be 2, 4, 6, 8, 10, and so on. That would never stop. So if I wanted to know, well, what is the sum of the first term, well, that would just be 2. If I said, what is the sum of the first two terms, well, I would take 2 plus 4, and that would give me my answer of 6. Or you can say the sum of the first 3, 2 plus 4 plus 6, the first 4, and figure out what that would be. So again, if a sequence goes on forever, we can limit it and just find the sum of the first however many we're looking for. Now, a series can also be represented using summation notation. So this is going to use the Greek letter sigma, and that's a capital sigma there. And that will denote the sum of a sequence defined by a rule as shown. So again, this symbol right here, this is going to be my sigma, and whatever is written in red there, that's the explicit formula for a sequence. Again, remember, an explicit formula that does not rely on prior terms. So you can find exactly what you're looking for just by knowing what term you are searching for in that problem. The first value of k, which we call our index, is given at the bottom here. So the letter that you use, that's called your index. And that should be the same letter that you see in your formula. And then the top number there written in green in this case is 5. That is the last value you would need. It doesn't always have to be 5, but in this example it goes for when your index k is from 1 up to 5.
All right, so let's take a look at an example of this. If we're going to use summation notation, let's write the series in summation notation. And so in order to do that, we would say we want to write the sum from k equals 1 to something, but we want to end up with 4, 8, 12. What do we notice about these? We see that these are all multiples of 4. So really, you could think of it as 4 times n, or 4 times, in this case, we're going to use k. So it would be 4k. So if I have k equals 1, my first term is going to be 4. If k is equal to 2, my second term is going to be 8, and so on. And I want to add this all up for the first 5 terms, because there's 1, 2, 3, 4, 5 terms. So we're going to say k equals 1 to 5, the sum of 4k for k equaling 1 to 5.
All right, and so that already is the notation for that one. So that first example is good there. So let's try another one of these. Given that my series is -1 plus 1/4 minus 1/9 plus 1/16 minus 1/25 plus 1/36. I want to figure out what that would be in summation notation. So first off, I want to figure out how did I get those different numbers that would have been in the sequence. So what would be my rule for getting a 1, 1/4, 1/9, 1/16, 1/25, 1/36? Again, we'll deal with the fact that it goes negative to positive in a second. So if you notice, we know that 4, 9, 16, 25, 36, those should kind of be, standing out to you that those are actually our perfect squares. So we have 1 squared is 1, 2 squared is 4, 9, 16, and so on. So my pattern here is going to be 1 over k squared, because that is going to be what term we are at. So the first term, we could really think of that as 1 over 1. The second term, 1 over 2 squared is 4. The third term has 1 over 3 squared, which is 9, and so on. So if I add this into my summation, we know at least that this is going to go from when k is equal to 1 to when k is equal to, well, we had 1, 2, 3, 4, 5, 6 terms. So that part 1 over k squared would get us the fraction that we have. We also need to deal with the fact that it goes from negative to positive. So over here in this box right here, it gives us a little hint on what we're going to do. So it says we're going to add in this portion here, negative 1 raised to the k plus 1 power, if your first term starts off as a positive. We will also add into our summation here, negative 1 just to the power of k if your first term is a negative. Again, that comes from having even powers of negative 1 would become positive, odd powers of negative 1 would stay negative. So in my problem here, my first term started off as a negative. It went negative, positive, negative, positive. So we will add in this rule right here because my first term was negative. So in my summation, I will also add in the fact that I need negative 1 to the k power, and that would help us get the alternating signs in my summation there.
Should we test this or show what the individual terms were, or no? It'll all just come back?
Yeah, we'll come back. All right.
Okay, so here's your first notes must do. You're going to write each series in summation notation. So 2/4 plus 2/9 plus 2/16 and so on. So you are going to start by writing some kind of summation notation, k equaling something up to something. You're going to fill in these blanks, and you need to have some kind of pattern here that it is following. And for this one, we're expanding the series. Let's take a look at this example. Expand the series and evaluate. So for this, if we are going k equals 2 to 5, and the pattern or the rule is 1 over 3 to the k, this is saying take 1 over 3 to the second, because I'm starting with k equaling 2, plus 1 over 3 to the third, because we're going to keep going. K values are going to keep going from 2 all the way up to 5. 1 plus 3 over 4, plus 1 over 3 to the fifth. I don't think I said that right. So 1 over 3 squared plus 1 over 3 cubed plus 1 over 3 to the fourth plus 1 over 3 to the fifth. So I get 1/9 plus 1/27 plus 1 over 81 plus 1 over 243. And when we add that all up, those four terms equal 40 over 243. And you can check that on your calculator.
All right, let's try another one of these for our examples. I always do that. I always choose the highlighter. Okay. So we want to expand this series. Again, we're going to use our index over here. So our k value is going to start at 1 and will work its way all the way up to 6. So we're going to add each of the values we get. So this will start off, and I'm going to use parentheses here to help us group this. So we'll have 1 squared minus 10, that's the first term, plus 2 squared minus 10, plus 3 squared minus 10, plus 4 squared minus 10. Let's see if I can move all this down for us for a second so I can add on the rest of them. All right, plus 5 squared minus 10, and finally, plus 6 squared minus 10. All right, so let's see what we would have here. We're going to end up with 1 minus 10, plus 4 minus 10, plus 9 minus 10, plus 16 minus 10, plus 25 minus 10, plus 36 minus 10. All right, so figuring out what we're going to have there, it looks like we're going to end up with, well, I'm going to do all my positives first, is how I'm going to combine this. So I know 1 plus 9 is 10, 4 plus 16 is another 20 added on to that, so I'm at 30. If I add on 25, that's 55, and then 36 to that would be 91. Mrs. Pesik's checking for me. Now, how many 10s am I going to have to subtract? Well, minus 10, 20, 30, 40, 50, 60, minus 60 from that total. So we're going to end up with a grand total that this is equal to 31. Okay, just a way for us to expand that series. So this leads you to your second must do. Expand each series and evaluate. Again, keep in mind here that your index, your k value is starting at 1, and you'll need to go all the way up to 4, and you will add each of those terms together that you get by plugging in each value for k.
Okay, so now we're going to find the sum of a series with many terms. Well, if we have many terms, it can be very tedious. So you can derive formulas for the sums of some common series. In a constant series, such as 3 plus 3 plus 3 plus 3 plus 3, that would look like this if we were going to write it using our summation notation. This is saying add 3 5 times. And that's really the same as 5 times 3, which is 15. So the formula for the sum of a constant series, so we don't have to just keep doing 3 plus 3 plus 3 however many times, there is a formula for that. And the formula is take the constant that you are adding together and multiply it by how many times you need it. Since we're going from 1 to n, it's really just going to be that number n times the c. So our formula for the sum of a constant series is going to be, if k equals 1 to n of c, it's just going to be n times c. It's going to be our formula for that.
Now, if we have a linear series, which means that we would have, powers of 1 in there when we are repeating our values. So linear series would be like the counting series, so such as the sum of the first 10 natural numbers. If I were to add all those up and look for a pattern, we could say that is a linear series, and we could represent it as the summation formula that if k is from 1 to n of k. So again, the most important thing here is you notice if you can rewrite this where your index is the same in, outside the summation and what the formula is, and that's k to the first power, then that is going to be equivalent to this formula, or maybe more oftenly represented as this formula. So again, if k goes from 1 up to n, and your formula, it just happens to be your index to the first power, linear, then we will expand that pattern by saying it is n times the quantity n plus 1 over 2. So again, if this went up to, 5, then I would just plug in 5s for all of my n values and calculate what that is. There's also one that is helpful for quadratic series. And again, when I say quadratic series, I mean that the rule for expanding that. So how would I plug in all of my values for the quadratic? That means that your index is raised to the second power in there. So again, all of these, the most important thing you need to make sure is that your index has to start at 1 if you're going to use any of these formulas here. So you always want to make sure that that is your starting point, and then you can use the pattern that it fits into. All of them rely on what that value of n is, or what the upper limit of the summation is. That is the number that you're going to plug in to each of the formulas given here. Okay, so we're just going to practice actually applying a couple of these formulas to a few problems. So again, just copy those formulas over for us again. Let's look at our first one. I want to evaluate the series that k starts at 1 to 10. So good thing pointing out that starts at 1, which means that that's going to be eligible to use one of these formulas. I notice that the number 6 is a constant. I do not see my k, my index, in the formula. And again, when I say formula, I mean this part in here. There's no k in there at all. So instead of writing out 6 multiple times and adding those all together, this is going to fit my first pattern right here. My c, my constant, is 6, so that's my c. And to figure out what this will equal, the series, it's going to be 6, my constant, times my top value, my n value, times 6. So this is equal to 60. Again, for this first one, just because it's kind of easy to see, if I were to list all these out, well, when k is 1, it would be 6. When k is 2, 3, 4, 5, 6, 7, 8, 9, 10. And if I added all those up, that would be 60. Now, the 6 wasn't too bad to do, but you wouldn't want to do that every time you had one of these, which is why these patterns are going to be helpful.
Okay, so let's try this example. If we are going to,
Adjust a little there.
there we go, excellent. So if we are going to evaluate this series, this time we have not a constant here, but we have a number that's going to be changing with the k. The k is changing, so this number is changing. So we could write that this is going to be 1 plus 2, right? Because k is 1, then k is 2, then k is 3, and so on. So this is not a constant, the same constant we're adding every time, and it would really go all the way up to, oops, I missed a number. So it would really go up to 8. So we could add all of these up, but there is an easier way. We can use this formula because, again, we see k here, k here. It's really adding 1 plus 2 plus 3 all the way up to our top number of n. And so we're going to use this formula. So that is going to be n. What's our n is our top number. That's 8. And what's our n plus 1 then is going to be 8 plus 1 is 9. And we're going to divide that by 2. So that's our formula for adding this. And so we'll get 8 times 9 divided by 2. That's 72 over 2, which is 36. And you could check that by adding these all up, but it's easier to just use the formula, especially if your n value gets large.
All right, and we have one more here we're going to practice. Again, this one, now this is a great example. We're going all the way up to 12 in this case. So we probably don't want to list out 12 of those terms and add them all up. So instead, I'm going to look at what we start with. Well, again, my k is starting at 1, which is good, which means these formulas could be helpful. I notice that my formula or my rule is k squared. Again, this k, that k are going to affect the change. So it's not a constant, it's not that first rule, but really it's going to match perfectly with this one up here on the end with the k squared. So in order to plug that form into that formula, I need to know my n value. My n is my top number on my summation, so my n is equal to 12. So this series is going to be equal to n, so 12, times the quantity n plus 1, or 12 plus 1, times the quantity of 2n plus 1, so 2 times 12 plus 1, all divided by 6. So again, I'm going to want to figure out what that number is. So if we start multiplying here, let's do our parentheses first and see what numbers we have. So 12 plus 1 right there, we're going to have 12 times, all right, that looks like a 13. And then we need to do 2 times 12, which is 24 plus 1. So this next one's going to be 24. And all of this is going to be divided by 6. So if we multiply 12 times 13 times 24, oh, it is 25. Whoops. I think I said that and I just wrote it backwards. Okay. So that's 3,900 divided by 6, which would give me 650. Okay, so that's the value of my series here. Again, that is the alternative to plugging in each of those k values and saying 1 squared plus 2 squared plus 3 squared, dot, 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 all the way up until I get to 12 squared, finding out each of those numbers and adding them all together. All right, so must do number 3. We would like you to try evaluating one of these series from k is 1 to 10 of k squared. Again, make sure you go ahead and see which of these formulas it would match with and use your top value of n, plug them in. If you want to list them all out and check them, you can do that as well to make sure you're on the right track. All right, and that's our end of our notes for 9.2.
Okay, we'll see you next time.
All right, thanks for watching.